Hello, my name is Sharon Finney, and this is my glider report for AE1601. Alright, so the requirements of the glider. So the glider must fit into a 16 by 16-inch box. It must be hand-thrown and not have any self-propelling technology. It must look like a glider. It must fly a minimum of 20 feet straight. And the glider must be primarily constructed of balsa wood. Alright, and these are pictures of my initial iteration of my design. For my first design, I wanted my glider to be relatively small, light, and nimble. The length of the fuselage was originally 12 inches long. For the wing geometry, I went for a slightly tapered straight design, with the trailing edge having a more aggressive taper than the leading edge. The wings have no dihedrals and hard, sharp corners. For horizontal stabilizers, I used a semi-elliptical design with straight trailing edges. The vertical stabilizer has rounded leading corners for increased aerodynamics. I constructed most of the assembly out of balsa wood. For added weight, I taped 6 small nuts above and below the nose of the glider, since the original design was very bottom heavy. For plane modifications, there were many changes I wanted to make for my final design. For starters, I sanded off the edges of the fuselage and gradually sanded off the top of each main wing to be like a true airfoil. Then I redesigned my two wings and my two horizontal stabilizers so that they have more refined rounded edges. To generate more lift, I glued my main wings at an angle of 5 degrees above the horizontal axis for a dihedral. Additionally, I angled the place of the horizontal stabilizers with a slight forward downward tilt. And finally, I chopped off an inch off the tail, allowing for the base of the vertical stabilizers to be flush with the end of the fuselage, and also reduce weight entirely. And this is my final iteration of the design, right here. Biggest change is the round elliptical wings. So there were three alternate generations and also the extra concepts. So wing shape was a big one. There are many other alternative geometries I could have done, including swept back, tapered, rectangular, delta, elliptical. My final design, I went for I hybridized elliptical and tapered. And for the wing placement, I opted to place the wings 2 3/4 of an inch from the nose of the fuselage. Having the wings closer to the front pushed forward the center of gravity, allowing for more forward weight distribution. If I placed the wings further back, I would have needed to add more weight to the nose to keep it balanced. And dihedral. Originally, my wings had no dihedrals, but in my final design, I opted for a slight 5-degree positive dihedral to generate more lift and stability. Having a negative angle increases maneuverability, which is not my goal for this project. Overall, I chose the alternatives with the highest probability of success, with also being experimental for my own fun factor. If I wanted more success, I would have added a more aggressive dihedral and a true elliptical wing geometry. For sizing, the glider is relatively short and small compared to others. The fuselage is 11 inches long, and the vertical stabilizer is 2.75 inches tall. And the design intention was to have a short glider with giant yet proportional wings. The horizontal stabilizers are a little small with the individual length of 1.9 inches. All of these were considered to generate a lighter aircraft that generates more lift. And the wingspan was 16.7 inches, the wing area was 41.5 inches squared, and NASA reach was 6.76 to 1. For balance, the most challenging obstacle during the design process was figuring out the weight distribution. The glider, although smaller and lighter than most, is bottom heavy. I needed to add a lot of mass to the nose to the balance out the mass of the center mass for it to glide and not loop. To resolve this, I taped 4 small nuts to the nose, and that balanced out the plane very well. The center of mass is now located even with the quarter of the wing. All right, and this is my test flight video right here. Let's see, I'm in the back wearing the gray shirt and the gray shorts. And here's my flight. All right, so my glider was the one that was thrown higher, kind of like more parabolic arc, as you can see. And it lands about the 30-foot marker. Mine's the one in the back. All right, so for the initial design of the glider flew approximately 22 feet. After making necessary modifications, which I explained already, my updated glider flew at an unofficial max distance of 60 feet. However, during the official competition, aka the video, it flew at the 30-foot marker. The glider flew with a parabolic arc before crashing and breaking in the grass, and one of my wings snapped off while that happened. And these are my lift and drag calculations. According to thin airfoil theory, the coefficient of lift is proportional to the angle of attack in this equation. And these are all my calculations. My average angle of attack is about 17 degrees for my flight testing. And my coefficient was about 1.87 for my lift. And for my drag, it was 0.366. Alrighty, so in short, the final design of my glider was a great success. It stayed within the bounds of the requirements, and it met the minimum flight distance needed to pass. Overall, it was fun designing my own glider. I got to take inspiration from others' designs, yet also got to research the ins and outs of how to make an efficient glider using different methods. Although the glider checked all the boxes, there are many ways that it can be improved. For one, the dihedral angle was, if it was more aggressive, it would have generated a lot more lift more efficiently. Additionally, the inclusion of elevators on horizontal stabilizers would have made it easier to produce more lift as well. And finally, true elliptical components, including wings, also the vertical stabilizer and the horizontal stabilizer, would have decreased drag overall and allowed for a more smoother flight. And these are my sources that I use. This has been my presentation and my report. Thank you for watching.